Hey, chemistry, it's Thursday, April 30th, and we're going to have kind of a rigorous lesson today, and so buckle up. I'm on page 484, and hopefully you've got your brain engaged. All right, I've got two sentences that are in italics, and I've highlighted them. Whoop. Let me just go ahead and hold this thing up. The sentence right here on page 484 says, the stronger an acid is, the weaker its conjugate base. The stronger a base is, the weaker its conjugate acid. And if you take a look at this equation right up here on page 484, that's hydrochloric acid. And you're going to go ahead and you're going to look at this table over here, table 6. And you can see that the acids get stronger as you go up. And you can see that the bases get stronger as you go down. That's the acid side. That's the base side. Okay, so we can compare things to see their level of strength on either side. And that's what we're going to be doing. Okay, so let's take that first equation. And that's hydrochloric acid plus water yields, well, we got hydronium ions, and that takes its positive with it. And you got chloride ions. Okay, so this is an acid. How do you know it's an acid? Well, it's got hydrogen on the front of it, but so does water. Yeah, water can act like an acid. Let's take a look at this table, page 485, table 6. Do you see water is way down here? And hydrochloric acid is way up there. It's a lot stronger than the water. So the water acts like a base because it's up against a bully acid, and that's a very weak acid. Okay, so it acts like a base. This is acid number 1, and this is going to be called base number 1. And the reason is because when this thing flies off, that's all you got left. It's called the conjugate base for that acid. And therefore, if this is the base, we'll call that base 2. This must be acid 2. And that's because the water gained a hydrogen with a positive hydrogen ion, and it became acid 2. You started this whole thing by saying, which one of these presents as a stronger acid? And it's this one, by far. And so therefore, this is relegated to being a base. Now, the acid-base conjugate acid-base pair are these two. Or the conjugate acid-base pair are these two. And that's why we put a subscript 2 next to that, subscript 1 next to those. All right, another thing you might want to do is compare acid with acid. When the equation is, this is an acid, and this is an acid. Go back to my table and tell me which one of those acids on the acid side is further up. Here's hydrochloric acid way up here. Here's the hydronium ion there. You'll notice that the strong acids are always got an asterisk next to them. And from below hydrogen down, none of those are strong acids. And so this hydrochloric acid is stronger than this acid over here, hydronium. So strong and weak. Now let's compare base with base. Well, I thought these were the pairs. I know. I'm sorry. I thought these were the pairs. Yeah, that's a conjugate acid base pair. Right now I'm not, and so is this one. Acid base pair. But I'm comparing acid with acid, and I'm comparing base with base. So let's go ahead and take a look at water compared to the chloride ion on the basic side. Here's water way up here. Oh, wait, it gets stronger going down, doesn't it? And where's chloride? Chloride ion is way up here. And so the chloride is a weaker base. Water is a stronger base when you put them up against one another. And so stronger and weaker. So it's always going to be strong, strong, weak, weak, or it's going to be weak, weak, strong, strong. Now, which way is the equation dominant? I would like for you to look at that last italicized sentence on the bottom of this page down here. You can see it in italics, and it says, proton transfer reactions favor the production of the weaker acid and the weaker base. So the dominant direction is toward the weaker side, and that's why that arrow is going that way. And it's 100% ionized because this is a strong acid. Any one of these will ionize 100%. These last two, and let's include hydroxide, any of these three bases will also ionize 100%. And so you'll only get one arrow going to the right. And but if it's a weak acid or a weak base, it's going to ionize going both directions. I mean, it's gonna drive both directions. Okay, so now it's 100% ionization because this has got the asterisk on it on the table. All right, so we've done page 484. 485 starts talking about this thing called an amphoteric compound. So when this water is up against hydrochloric acid, it doesn't act like an acid, even though it's listed on the acid side. It's also listed over here on the base side. It can go both ways. It's ambidextrous. It's a switch hitter. So it is a weak base. It's a weak acid, but when you put it up against a strong acid, it acts like a base. When you put it up against a base that is a base that is stronger than it is, it's going to act like an acid. Okay, so let's go for ammonia. NH3 and water. And I think you have that equation on page 486. We got ammonia and water, and it's going like this, and it's taking one of the hydrogens and attaching it to this thing. Instead of that arrow going like this, it's going like this. And you're going to get ammonium ions, NH4, positive 1, because now you got 4 hydrogens, and it brings its positive with it, proton transfer. And then you got this thing, what's left after you take a hydrogen out of there is hydroxide. And that hydroxide is indication you got a base. Now, is ammonia kind of also on the acid side? Ammonia, way, way, way down here on the acid side. And so it's a really weak acid. Water is just above it. Water is a stronger acid, which relegates ammonia to being the base in this equation. All right? Now, when the proton transfer occurs, you make an acid. And so this base and that acid go together. Base 1, acid 1. And this acid and this base go together. This is acid 2, that's base 2. Okay, so now here's the question. Let's just compare the acids. Let's compare the bases. Which one, by the way, how did I know that water was acting like an acid here? It's because this is also on the acid table and it's weaker, which means that this has to be the base. All right, now this is the acid. And let's compare acids. Water and ammonia. There's water down there, and ammonium is up there. That's an acid, And typically the positive ions are acids and negative ions are bases, but not always. I'm going to show you that in a minute here. Okay, so ammonium then is a stronger acid than water. And this would be weaker. That's all you need to know, because you can fill in the rest. That's going to be stronger than this. And so it's going to be weak, weak, strong, strong, or it's going to be strong, strong, weak, weak, but it's going to be that way. Those are your options. And the acid-base pairs are this with this, and that with that. Okay, now this is ammonia, so it's a weak acid, it's a weak base, and so it's a two-way arrow. And most of the solution is molecular. And this is the stronger direction. So the quantity of molecules is greater, the quantity of ions is less. Okay, that there's one more thing I wanted to talk about. Let's see how long I've talked. 17, 27, 10, 11 minutes. Okay, wait, I get to do it 2 more minutes, okay? Because I want to do one more thing. Here we go. How about an acid that looks like this? That's carbonic acid. It's coming out of my mouth right now because I've got saliva that's water and I got carbon dioxide gas and they're mixing in my mouth. I've got an acidic mouth. Okay, and then we're going to combine that with water and we're going to form hydronium ions. Here we go. That means those are acidic ions. And what's left behind when you strip off a hydrogen is HCO3. And it's negative because you're taking your positive with it, so it leaves it down one. Okay, and so we're going to go ahead and take this, which is, this is the acid, because it's donating protons, and this will be the base, because it's receiving protons. And this is going to be the acid that is formed. And so this is a conjugate acid-base pair, and this is a conjugate acid-base pair. That's acid 1, this is base 1. 1, because it's the first thing we come to left to right, and this is 2, and that's 2. And this is a 2-stage ionization. The second stage takes this, you can see that it's got a hydrogen right there, so we can strip that baby off. And we can add water to it, and we can make hydronium ions. Here it goes. And what's left behind is carbonate, which is 2 negative because it's down 2 now. So what is HCO3, -1? Is it a base or is it an acid? It's amphoteric, guys. It's either a base or an acid. Now up here, this is a H2CO3. You're going to find it way down here. H2CO3. There it is, carbonic acid. It is not strong. And then where's water with respect to that acid? Water is H2O down here. So it is a weaker. It is weaker than this weak acid. So therefore it plays the role of being a base. So water is amphoteric. Well, it doesn't show you that because it's base there and base there. Okay. Anyway, so that's a, and by the way, since this is a weak acid, it's going to be a 2-way arrow. This is going to be a 2-way arrow. And a 2-stage ionization, you get hydronium ions in greatest quantity. And the one that is in least quantity is carbonate ions, because that's the second stage at the end. Most of the ionization is done during the first stage. See you later.